Okay, we're going to now finish up 1989 AB2's number question, specifically part C. And in this case, the idea is we're supposed to take this particular looking graph, y equals radical 6x plus 4, y equals 2x, rotate it around this line here so that it would look something like this, revolved around. If I'm going to do it with relationship to x, so I want to make this a dx problem, you'll have to realize that I am not doing the disk method. I am actually using cylindrical shells. The reason I'm using cylindrical shells is, let's write it over here. For instance, when my value of x is very close to 0, I'm going to have a very tiny little shell, a narrow shell, that's going to go about yay high and come almost all the way down to the bottom. As I go slightly farther out, the upper part will increase, but I'm also going to be cutting off the bottom, and then it's going to look like that. So it'll be looking like it's hanging midstream. It's not going to go up as high on the top, as fast on the top, so that's going to come out, but it is going to rise faster and being cut off on the faster on the bottom, to the point where near the very end it's going to look like almost a ring. It's going to be very wide, but very narrow because most of it's cut off, and it's going to look like that. Okay, so the idea is I need to figure out a formula for radius, and I need to figure out a formula for height. Well, in each of these cylinders, my height is being determined this way. And I can see that radical 6x plus 4 is my upper height, or outer. 2x is what I use to cut it off. That's my inner, or lower. I also realize that when x was 0, I had 0 radius. If I had x at a half, my radius was a half. When my x is 1, my radius went out to be 1. And so therefore my radius actually is x. Therefore, if the formula for a cylindrical shell is v equals 2 pi times the integral of the radius times the height, because that is the surface area of a shell, and we do need area for a formula, dx, then I'm going to say that the volume is going to equal 2 pi the integral from 0 to x, because that's my radius, times the height of 6x plus 4, oops, that's too much there, minus 2x, and then dx. And I've done this already on the calculator. I've done it with using the F and N key, say 3.081481 pi. I've worked that out as a fraction. I've seen that to be 416 over 135 pi. I have also plugged in pi and came up with 9.680759 units cubed. However, I know this is what the problem says. It says set up but do not integrate. Well, we've already integrated using technology means. We are going to practice integrating doing the old-fashioned way. And the reason I want that practice is because of the following. If I break this up as two separate shells, a shell that represents the top part being cut off by a shell that represents the bottom part, I'm going to just say right now, I'm not going to spend a lot of time on this one because I already know all the work. It's negative 2 pi times the integral of 2x squared dx, which is negative 2 pi times 2/3 x cubed from 0 to 2, and this works out to be negative 32/3 pi. So this piece right here already worked out. I was never really too concerned about doing the integral of that piece. This one, on the other hand, will require some special techniques. However, the first technique, use substitution, makes perfect sense. That fills into that spot right there. The du would be 6dx, but unfortunately I would want the 6 on the other side, so it would be 1/6dx. I have a perfect match here as well. The problem is I have not successfully gotten rid of my x. It is still here. I need a way to get rid of it. And right now I don't know how to do that. That's why I'm putting a little question mark. But I have an idea. I'm going to actually borrow from my u equals 6x plus 4 and realize if u can equal something something x, then why can't x equal something something u? For instance, u minus 4 could equal 6x, and therefore 1/6 the quantity u minus 4 could equal x. Well, since x is what I want to substitute with, I could actually plug this into that spot right there. And this would produce an integral of the following. This integral could be rewritten as v equals 2 pi times, now in where the x goes, I'm just going to put a big giant bracket, 1/6 u minus 4, because that was the x. In the 6x plus 4 spot, I would just put u to the half. And in the dx spot would be du. The only thing I would need to figure out are what my new limits are, and that's not too hard. The new limits would be 4 and 16. So, if I rewrite this problem, which I'm going to write over here, I'm going to move everything. Oh, I forgot a very key piece. My du, I would also need to have a 1/6 in front of that as well. Sorry, I forgot about that right there. So, if I'm going to do this, then I'm going to move all my pieces here, 1/6 and this 1/6 in the front, and I'm going to come up with pi over 18, because 2 pi times 1/6 times 1/6 is pi over 18. I'm going to write 4 to 16 as my limits. I'm going to write this as u minus 4 times u to the half du, which means I'm really going to rewrite this as pi over 18 from 4 to 16, integral from 4 to 16 of u to the 3/2 minus 4u to the 1/2 du. That's why I'm spending so much time on this problem. I already know how to write the formula, which is all the problem asked. That's way up here. I want to learn a new technique, which is finding a way to get other numbers like u in to fill in some of these missing gaps. So, if I do the antiderivative of this, that is going to be pi over 18 times 2/5 u to the 5/2 minus 8/3 u to the 3/2 of going from 4 to 16. So if I plug in my numbers, which I will do for demonstration purposes, 2/5 times 2/5 times 16 to the 5/2 minus 8/3 times 16 to the 3/2, and then I subtract that all by 2/5 times 4 to the 5/2 minus 8/3 times 4 to the 3/2, I will be able to get the answer that I am looking for above way on top. And that is as follows. Pi over 18. Let's just say I have done this way ahead of time. And all this worked out to be 1856 over 135 after I multiplied the 18 into this piece. So technically, this is 1856 over 135 pi. And I believe I still have to do this piece over here. Now I'm not exactly trusting myself. Let's try this out. 2/5 times 4 raised to the 5/2 minus 8/3 times 4 raised to the 3/2. And this piece works out to be negative 128 over 15. No. Let's try it again. Big mistake here. I forgot to multiply this by pi over 18. So multiply that by pi over 18. You actually get negative 64 1/35 pi. All right, let's see what we come up with. Okay, I've gone back and realized I actually gave you, I believe, which is the final answer for this whole thing here. I actually went back and revisited, and this is 1792 over 1/35 pi, which is then subtracted by a negative 64. So I will subtract a negative 64 divided by 1/35, and that does work out to be my 1856 over 1/35 pi. So this answer that I gave you originally is actually the final answer of this whole piece right there. That's what that is. But that piece still needs to be subtracted, because that's what this piece is. That needs to be subtracted by 32/3 pi, and that should not be drastically different when you realize that this really needs to be multiplied by a pretty large number. Looks like it needs to be multiplied by, what, 45? Top and bottom. So when I'm all done and I subtract those two, it does work out to be a 416th over 135 pi as your final answer, which is what you got here. So in this particular page, the C I was doing was based on cylindrical shells. This is your setup, which is all the problem I ever asked for. But I did work it all out so that you can learn this technique right here and come up with an answer of 416 over 135 pi. And you can work it out. And that's enough for this page. So I'm about to do this all over again for C. So onto a fourth page, except this time we will use the disk method to actually figure this out. Alright, we're going to finish up 1989 AB number 2, but this time we're going to look at it from a disk method, because the shell method was dx, this will be a dy problem, and that will require us to realize that we're going to have to do a little rewriting of the graphs. First, if y equals the square root of 6x plus 4, after squaring both sides, subtracting the 4, dividing by 6, I can say 1/6 times y squared minus 4 will equal x. And the weird thing is that is going to be this piece right here, which is the inner piece, but it's only the inner from when y is from 2, y is, 2 to 4. Because this graph starts at 2, goes to 4. My other inner is actually the y-axis, and because it's the y-axis, I can tell you that, that's the line x equals 0. And that inner only applies from 0 to 2. In all the cases, my outer, which is over here, can be figured out as y equals 2x, or more importantly, 1/2 y equals x. So if I want to attack it with the disk method, because I'm very comfortable with the disk method, then I'm going to have to remember that I actually have to write two integrals. The first integral is going to go from 0 to 2 of what would be the outer piece. I'll write as y over 2 quantity squared, and then minus 0 quantity squared, and that would be my radius. Each of my radiuses squared, and then times pi. And then I would have to subtract, or add, let's be clear, another integral that goes from 2 to 4 of pi. And if I want to move ahead on this, it'd still be the same outer y over 2 quantity squared, but then my inner one would be minus, and I'm going to put this as a fraction, y squared minus 4 all over 6 quantity squared dy in both cases. Okay. 0 is not important, so what I'm really going to do is from 0 to 2 of what would end up being 1/4 y squared dy would then be added to the integral from 2 to 4 of, again, 1/4 y squared minus, and, well, if I pull the 1/6 out and I square it, then I just have to do y squared minus 4 and square it. And so that means this is 136 times the quantity y to the 4th minus 8y squared plus 16. So if I really want to break it each down, if I'm subtracting each one of these pieces, because that's what I'm doing here, this is all being subtracted to there, I'd be subtracting 136y to the 4th. I'd be adding 836. I'm just going to write that down, 836y squared. And I'd be subtracting 1636. And that whole thing would be raised to the dy, or would be dy. Okay, so the antiderivative of this piece is going to be 1/4 times 1/3 y cubed, going from 0 to 2, all multiplied by pi, which is the same as 1/12 y cubed from 0 to 2. And very quickly, that would be 2 cubed, which is 8, 8/12, which is 2/3. So this whole piece works out to be 2/3 pi minus 0, and so that is this piece right there. The other piece I have to do the antiderivative for, so it's going to be, again, 1/12 y cubed, except now this piece is going to be 36 times 5, which is 180, so negative 1/180th y to the 5th, plus, this will go to y cubed. 36 times 3 is 108. 8 divided by 108 works out to be the fraction of 2/27. Oh, this looks like fun. And then minus 16/36, which works out to be the fraction 4/9. And this is going to go from 2 to 4. I see this now that 4/9 is actually 4/9 y. That would have a small difference. Okay, what I've done is I've plugged 4 into all of this, and it comes out to be 352 over 135. I've plugged 2 into all of this, and I come with minus 26 1/35. Therefore, 352 minus 26 should be 326. This particular piece is pi times 326 over 135. So if this is what this piece represents, then I just have to take 2/3 pi, add it to 326 over 135 pi. So here goes everything, 2/3 plus 326 over 135. I hit frac, and lo and behold, it works out to be the exact same 416 over 135 pi. 1989 has a lot of parts. My time is up. It's good enough as any. Enjoy.